So this is our third part in this series. If you guys aren't familiar with this, how discussion series work on this channel, every week usually, we're trying to get it down to a weekly schedule. Every week we meet here and go over some of the material of a topic that you guys picked that you said you wanted to learn about. This week, or this topic that we're working about is classical field theory, and this week we're on part 3, which is mostly about the Lorentz transformations, which is a very important concept because soon we're going to go from the Lorentz transformations into, next week we'll be doing 4 component
now
vectors.
You're recording time for useless speaking comments.
Right, exactly. So next week we will be starting 4 component vectors, and 4 component vectors, in my opinion, are like the bread and butter of field theory. But maybe that's the, maybe someone else who knows it better might have a different opinion of that. Let's talk a little bit about what we did last time, which was several weeks ago, considering we had to take some weeks off for break, and then I was supposed to stream on Wednesday before Christmas, and I got pulled away because of family, which was good. But if you are unfamiliar with this, we do meet here and probably Wednesdays right around this time. And the notes are available for today, ! Notes in the chat. If you'd like to get those on the Google Drive, navigate to the classical field theory folder, and I have made them available there. They are also on the Discord, ! Discord, if you want to get them later. And if you're watching on YouTube, they'll be down in the description below. Okay. But let's talk about last time, what we did 2 or 3 or 4 weeks ago, whenever it was. We were finishing up on intervals. We were going over intervals in space-time, and that led us to find some invariants of intervals. That was kind of like the key takeaway last time, was if we had some, c squared t squared minus x squared, in a 1 plus 1 dimension, 1 of space, 1 of time, then that had to be equal to a c squared t prime squared equal to x prime squared. The intervals in either of these had to be equal. That was what we established, both as discrete and as infinitesimally small intervals. So that was kind of the end of the intervals discussion, was trying to make sure that we had that clarity in that. And then we also went into talking about the proper time, so time as it's measured in a moving frame of reference from the point of view of a stationary reference. And then we ended by saying the Galilean transformation when we started the Lorentz transformation. So for and I want to write these out because these are going to be important. So the Lorentz transformations. And we're going to talk a little bit about discrete symmetries when we talk about CS Woo as well. So this is, we're not going to go deeply into any of the discrete symmetries. That may come at a much later date, I'm not sure. But we'll talk briefly about Lorentz symmetries and symmetries in general, and the Lorentz transformations. But we talked earlier about Galilean principles of relativity, and along with the Galilean principles of relativity, there were the Galilean transforms, which I introduced last time. Transforms. And these are the ones that we want to update. We noticed that they had some issues last time. So x is equal to x prime plus some velocity of the frames moving times t. And then we had y is equal to y prime, and z is equal to z prime, and then t was equal to t prime, because t was just a parameter. It was just sort of like this thing that we don't care much about. It can't really change. Let's see here. You still have not jumped to natural units. Really crooked. Is it really crooked? I'm terrified to touch it. Oh, it is kind of crooked. Hold on. Oh, no. Let's try that. Maybe that's a less crooked, but I don't know. It might be warped. But it's also like wide angle, and it's like I'm kind of far away. So we'll just go with that and see what happens. Yeah, I use weird metrics. So I'm following the book. Oh, by the way, the book that we use, if you're new the first time, the book that we're using is L&L, Landau and Lifshitz, the Volume 2, Course in Theoretical Physics, Volume 2, which is the Classical Theory of Fields, which was a request by y'all to use that. So these are the Galilean transforms, and we found out that these are not invariant. That was the key takeaway when we left. We wanted invariant intervals, and the Galilean transforms did not work once we started including that we had a maximum speed limit of the speed of light and everything that followed from the, the updated principle of relativity. And let's get into our part 3 now, and that is we want to talk about intervals. And we talked about intervals being translated. That's what the idea was when we talked about intervals, moving along. We have, how is something going to look in a frame of reference as it's moving along, some path. And we talked about all of that. But now we also need to be sure that we can talk about rotations in this, in these two, with Lorentz transformations, or transformations in general. How is something going to look if not only am I looking at it, but instead I rotate and still look at it, right? What is that going to do when there's another object in motion? So again, we're going to consider our two systems. We have our system K and our system K prime, which the system K prime is going to be the one that's moving. And we can even just say, like, if I were to rotate in, let's consider, I guess, our three-dimensional like Cartesian space, right? That's the thing that we're most familiar with, x, y, and z coordinates, right? There are 3 planes in an x, y, and z coordinate system. There are the planes x, y, z, zx, right? Those are the planes. And rotations inside those planes should not change any laws of physics. That's a common thing. Right, so rotations inside those planes should not matter. So now we have a 4th coordinate that we are adding, which is time, and we are going to now have 6 planes that let us rotate, right? So what we're going to do is we're going to consider one of the planes, and that's the tx plane. Of course, if we're going to just consider like an xy plane, that's not going to do us very much justice because, well, it's the same thing as the Galilean transforms, right? Like that happens when you consider just like an x and a y plane. But now we need to include time. So what if we rotate in the plane of x and t? So we'll rotate in this plane. We have to leave this invariant. That has to still be true, the rotation in the tx plane. The intervals still need to be true. So let's talk about what those relationships are. Of course, we need to get some hyperbolic trigonometry involved in this because we have this minus sign, right? That's not as straightforward as if we were to just do, the Pythagorean theorem. So we have to do hyperbolic trigonometry. So x is going to be equal to our x prime. And again, our 2 frames of reference are k and k prime. K prime is moving. We'll get there in just a second, how they're moving. But let's just write out the general transformations from coordinate to coordinate. Psi plus ct prime, sinh, psi. How do people say it? Do they say cosh and sinh? I don't know how y'all say. I'm probably going to say cosh, sinh, and hyperbolic tangent. Sinh psi plus ct cosh psi. Now, again, we want the invariance of the interval to be true. So let's consider k prime. What'd you say? Tang? Oh, no, not tang. No, tang is fine, too. Cosh, sinh, and tang. I don't know. Tang always rubbed me the wrong way. It was always just like, why tang? You know what I mean? Cosh is like the ball. Sinh is like, pulling a knot tight. Tang, it's not a thing. It's not a thing. Let's see here. So if we consider k prime to be moving in k, so we are in k is the rest frame, k prime is moving, and we're going to be concerning ourselves with... No, don't go. Come on, I didn't... Stop it. Then we're going to be concerning ourselves with the k prime origin as the thing that's moving. So we can make sure that we can set x prime equal to 0. And now we can simplify our equations here. This is going to be a lot of equations today because we're going to be moving things around and simplifying them to get the real type of transformations that we need, right? Our goal today is to prove that the Galilean transforms don't work. And well, we found that out last time, but we're going to find transformations that do work, that treat time as this coordinate that needs to be. And in order to do that, we need to take a look at a rotation in the x and t plane. And like I said, the sign, this is pretty much, I like to think of this as the same concepts of the Pythagorean theorem, except with hyperbolic trigonometry. But maybe, like I said, there might be someone who can, I think that's kind of a cheater way, but maybe that's fine. So let's write these coordinates down. X is equal to t prime hyperbolic sine, and ct is equal to ct prime hyperbolic cosine. And now we can go ahead and, did I write that in the notes correctly? Hopefully I did. Because I didn't write it in my notes correctly. But I think I did in the notes. If there's any errors that I need to fix after the lesson, make sure you let me know, and I'll just hop in and do that after I get off of streaming. If we divide these equations, we can find that x over ct is equal to, the ct primes are going to cancel away, which is really nice, and then we get the hyperbolic tangent of psi. And the hyperbolic tangent of psi, well, so what's this? This is just going to be the velocity, because as x is changing in time, is just going to be the velocity over c, and now we're talking about the two systems, the one system moving in reference to the other system.
On the blackboard, you have an extra prime on quart second equation from the top.
Oh, you're talking about here. I see. I was talking about the notes. So then we can go ahead and we can find what these are going to be. If we want to split the tangent back up using our laws of hyperbolic trigonometry, our goal is to get back into this equation. So in order to do that, we could split up what we know about the hyperbolic tangent into separate equations, where we have the sinh of psi. Let's do a little side calculation here. It's going to be equal to v over c divided by the square root of 1 minus v squared over c squared, and then cosh of psi is going to be 1 over the square root of 1 minus v squared over c squared. And those are going to be our two hyperbolic functions. And doing that, and of course that is, pretty much the same thing as just dividing by or multiplying by 1 in this equation. But in doing that, we can then find our substitutions for these equations, which is the goal, right? Or even one more, our substitution for this equation right here. That's better. That's what we want to do. And what do we get? Well, we get x is then going to be equal to x prime plus vt prime. There's a prime already there. Square root of 1 minus v squared over c squared. And then we have y is equal to y, z is equal to, y prime, z is equal to z prime, and then t is equal to t prime plus v over c squared times x prime divided by the square root of 1 minus v squared over c squared. Did I get all my squares right? I better, or else I'll get roasted. So these are the Lorentz transformations, and that's what the goal of today was to find, most of the goal of today, Lorentz transformations. Now, if we are going to carry out these transformations, we'll find that the intervals will remain invariant. That was based off of this rule. Check. We've checked all the boxes, and we found that that is true based off of what we found with these two invariables and this rotation. So now, anytime that we apply these transformations, we do get that. Nice, clean interval invariance, and that's the goal. So what we get today is, another thing that we can think about today is what is the relationship between the velocity of the frames of reference and the speed of light. So that's a very interesting relationship, one that we should look at really quickly, okay? So let's take a look at the relationship in the x frame, or the x direction. And I guess in the t direction is the same thing. Let's set v greater than c. So what happens if we let v be greater than c? Well, then this number becomes greater than 1, and we get this 1 minus something becomes negative, and then we get the square root of a negative number, so that's imaginary. Okay, and we already had this restriction that v could not be greater than the c. We had space-like, we talked about it in several different ways. We talked about space-like separation and ultimately how that caused things to not be causal, but now we also see that we get imaginary numbers in these transformations if we allow v to be greater than the speed of light. So v has to be less than the speed of light, and then what happens if we let c go to infinity? Okay, now that's kind of like, what you might what you might be confused about a little bit if we let c go to infinity, but if we let c go to infinity, this becomes 0, so we get 1 minus 0, so it's the square root of 1. This term also becomes 0, and we recover the Galilean transforms, which is a very unusual thing, right? Because then we get this c also equals 0. That goes away on the denominator. We recover the original top equation as well. So when c goes to infinity, or very, very, very large, we recover Galilean transformations. And there's more to that, too, as well, as we're going to see in a second. Now let's talk about the next step, which is length. We need to talk about length. Oh, so when the Lorentz transformation has an imaginary number, everyone loses it. But when the Schrodinger equation, everyone just collapses. That's good. Isn't Dirac didn't clap, right? Easy clap. Okay, so that's really funny. So now, if we want to talk about lengths, we can talk about these coordinates and how they're going to be changing. Because coordinates is really just measuring a distance or a difference in between two coordinates, right? So we're going to be using x2 minus x1 and then x2 prime minus x1 prime. So let's write those down. We want to talk about a length of a rod at rest in a system with delta x is equal to x2 minus x1. And this is in, K. And now we're going to have another system, delta x prime with x2 prime minus x1 prime. And this is going to be in K prime. It's supposed to be in as well. In K prime. And these, feels weird, man, clap. And these distances are going to be different, right? One's in motion. That's the big deal. K prime's in motion. It's going to be measuring the length of the rod in its own frame of reference and to find that it's going to be different. But how do we find out whether it's how do we find out how different it is? And that's as easy as just using our Lorentz transformations. So if we have our x1 reference, this is going to be x1 is equal to x1 prime plus v t prime divided by the square root of 1 minus v squared over c squared. Our x2 is going to be x2 prime plus v over t prime divided by the square root of 1 minus v squared over c squared. And then lastly, we're going to have our delta x is equal to delta x prime divided by the square root of 1 minus v squared over c squared. Now, this is pretty straightforward. Once we subtract the two, subtract this from this, the VTs get subtracted away, and we just have x2 prime minus x1 prime over our denominator. And then we can rearrange this thing, redefine some labels. What do you say, x-pop and t-pop? K-pop, stop that. Stop it. Stop K-pop. Then what happens if we redefine the variable? So let's call this the length in the K prime frame of reference. Oh, I'm sorry, in the original, in the at rest frame, and then this in the frame of reference in motion. And we can talk about the proper time, L, of something by referring back to it in its rest frame as that following equation. Okay, and this is straight from the book. Hi, commentator. I have not hurt myself yet. So this is the proper length scale. Now, it's pretty straightforward to take the proper length scale and turn it into proper volume because, of course, when something is in motion along a singular direction, then we don't worry about changing any of the other coordinates. The transverse directions do not change. So, therefore, it's pretty much a straight transformation to the volume. Proper volume of something as it appears, c squared can be given as that. But this is kind of like, we should take a second to just imagine how strange this is. Like, this is a really strange thing, and I don't think people think about it enough. Like, I have a cup. Okay? That's not the end of this either. Okay? That's just the beginning. I have a cup. Okay? And it has some volume to it. It holds water. Right? A certain amount of water. Okay? Crazy, I know. Crazy. Okay? But now, if I'm... Free cup trick. But now, if I'm in motion... Why am I doing the cup trick? if I'm in motion, okay, moving in a linear motion, along some axis, the volume of my cup is going to look different. That's strange. That should be really weird. He did it. Yes, that's the cup trick. I think it's still very strange that once I become in motion, that cup just looks very, it looks very strange in comparison. It looks very strange in comparison, especially the faster you go. The faster you go, the difference the volume is going to be. What's the difference? What's going to be this difference? Can we get an idea of what this number is going to be like? Well, sure. So if v is, relatively close to the speed of light, then this number is going to be very, 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 very small, right? So it's going to change the volume from its normal volume, from what we see at rest, which is just here, to something that's incredibly small. And I think that's very odd that is happening, right? And it makes me think of like the relativistic particles, how skewed up is our notion of the shape of those, right? And I think that's not something that's beyond physicists. Physicists have been working on that for a while, and understand that. But you're starting to realize why I hope you're starting to realize why relativistic information is very important to understand, especially when it comes to the realm of like quantum computers and stuff, is because of how odd certain things behave, right? And this is all classical. We haven't even talked about quantum mechanics stuff yet. So volume does transform like that, and then we also have another thing. Oh, and then proper time. Proper time, we should mention that. We talked about it a little bit last time, but we should mention it again. Delta t now transforms as delta t prime divided by the square root of 1 minus v squared over c squared. Oddly enough, as you might imagine, it transforms just like space does, right? So that's what the goal was, right? To get that, to get the idea of how time is going to be a lot more like space in this scenario. Okay, so let's start the next section. Transformations. Formations of velocities. This is going to be what we'll end on. We will not be getting to four vectors today. We will start 4 vectors next Wednesday. But the transformations of velocity. So what would motion look like if we were let's try again. So what would motion look like to observers in K relative to K prime? So say I see a particle, the motion of a particle, right? And I see it traveling off in some distance, and I start to calculate the velocity of that particle. Well, I'm going to calculate that velocity of the particle. Someone in K prime is going to calculate that velocity of the particle. I'm going to calculate how it's moving in reference to K prime, and K prime is moving with different length scales, so it could be some difference going on, right? There could be a lot of differences going on between those two things. Suppose if we were to use how did you measure velocities when you were taking your labs in undergraduate, right? Well, you set up some...
You have an extra naught in the volume transformation.
Good catch. Thank you. I was being overly naughty. So if you remember your introduction labs, there was, how did you measure velocities? Well, you could measure by taking some distance that you knew and marking off a time when something passes one point on the distance and a time that it passes another point on the distance, and then measuring the distance in space over the distance in time. But now we're finding out that distance in space and distance in time are different things in different frames of reference. So we need a way to talk about how velocities are going to transform under this Lorentz transformation as well. In order to do that, we should revisit our transformations, but this time we want to make them infinitesimal in nature. Remember, I told you that infinitesimals are really, what physics is all about. That was a lesson taught to us by Newton, which, I guess we can give him a pass for how he botched up relativity, but I guess we'll forgive him. And then let's see. So we have dy is equal to dy prime, dz is equal to dz prime, and then dt. Of course, these are all the same things. Just now we're talking about infinitesimals and how it changes infinitesimally. And that way we can start comparing velocities and how velocities are going to be changing of objects. it's not so good to get pigeonholed into a theory where like you can't address all of physics. And special relativity is certainly not one of those theories, you know. You can address all of these problems. Okay, so now we have our infinitesimal. So if we want to set up any of the velocities, it's as easy as dividing dx, dy, dz by dt. You know, whichever way we want to set it up, we can do that very straightforwardly. Let's write them down. I have the velocities of particles in a frame of reference are given with subscripts. The velocities of the frames of reference are given without subscripts. So k prime is moving at a velocity of v with respect to k, and inside of these systems there is a particle that is moving along with some velocity given by dx, dt, dy, dt, and dz, dt. Vx prime plus v. Again, we're just dividing the two, so dividing this by this. And this is what we're getting as a solution to all of these. 1 plus Vx prime V over c squared. And then Vy is equal to Vy prime times the square root of 1 minus V squared c squared divided by 1 plus Vx prime v over c squared. Notice how these both have vx primes in the denominator. That's a result of dt existing like this. Because again, the k prime is moving in the x direction. Of course, it would change if k prime was moving in a different direction. But that was how we started this, was k prime was moving in the x direction. V squared over c squared, all divided by 1 plus vx prime v over c squared. Now you might be wondering, why have I written all of these out? Well, it's also an interesting thing right now to consider the following. I guess what we could do, Nani, more. I guess what we could do, oh, hey, Puzzle. Good to see you. I guess what we could do is...
has had 5 accident-free days.
I have had at least 5. We could write down the velocity relationship if the particle is traveling in the x direction. So let's do that, and we're going to see something kind of interesting. So if the particle is traveling, I don't know how many L's are in traveling, in x direction, this simplifies to the following. Okay? And we'll write it up here. Simplifies to the following. The velocity then becomes Vx plus v over 1 plus Vx prime v over c squared. And what happens now if we're talking about, and this is one of the reasons why we can give Newton his break. We can cut him some slack, okay? You know, it turns out, you know, he just wasn't bright enough, okay? And we can do that by just saying, okay, well, what if the motions are all dramatically lower than the speed of light? Okay? If they're all dramatically lower than the speed of light, then this term dominates. Vx and v are similar. They can be similar, of course. But the c term is going to dominate. This is going to go to 0. And we're going to find out that any velocity, oh, this is supposed to be primed, excuse me. Any velocity is just going to be equal to the addition of the velocities, which is true in Newtonian physics, but it's also not true in approximately. Let's say approximately. Okay? And this is why we give him his pass. Because ultimately it's close, but it's not the same thing. There's some big differences between the two, right? And we found that out, right? C is a real thing that we have to be very concerned about. So so if we start to get velocities that are faster if we're starting to get velocities that are much faster than the speed of, closer to the speed of light, I should say, then these are going to be some non-negligible effects. Close, but no cigar, exactly. All right, that's it for today. Next week, we're going to talk about 4 components. So these are all everything to do with Lorentz transformations, right? We want to make sure that intervals don't change under these transformations. That's a very important thing, and that becomes one of the crux of all physics, is that nothing changes under a Lorentz transformation so long as it's real, right? We want to make sure that we preface that because good physics can be done with systems that break Lorentz invariance, but they won't be real physics. They'll be, it'll be more about learning about other systems and stuff like that. But that's it for today. Ouch. It appears we have some questions. Well, you set up some...
You have an extra naught in the volume transformation.
Good catch. Thank you. I was being overly naughty.